Hello, my name is Joe Tate, and I'm a retired electrical engineer and inventor. My newest invention is a wave-powered pump for seawater desalination, the goal of which is to cheaply purify water for human consumption and agriculture. Water. Water is a prerequisite for life as we know it. Although it's vital to our existence, we mostly take it for granted. Our modern infrastructure has delivered safe drinking water to our homes without fail for quite a long time. We've only to turn a valve to avail ourselves of this vital liquid anytime. Is there anything we can do in places like California, where we only have maybe a year's worth of water left? Many have suggested building desalination plants to purify the boundless seawater of our oceans. However, critics have pointed out the enormous power requirements and fossil fuel dependency of these systems. Modern desalination works by bringing seawater to a high pressure and forcing it through a reverse osmosis filter. The RO filter will allow water molecules through, but not the salt molecules. Incidentally, it takes about 8 kilowatt hours of energy to make 1 gallon of water. At 15 cents per kilowatt hour, each gallon of water costs about $1.20. That's just for the energy. California users now pay 0.3 cents per gallon for delivered water. So you can see why fuel-driven desalination isn't practical. The energy costs are just too high. By looking at the problem in a different way, we may be able to overcome the aforementioned objections in a simple and sustainable way. If you look at an ocean shoreline, we observe large energetic waves crashing on the shore. These waves, which might be thought of as concentrated wind energy, embody enormous power that can be harnessed to purify water. All the needed energy for desalination can be supplied by waves right at the point of freshwater extraction. By absorbing the energy from the ocean waves, dependence on fuel or electricity is eliminated. This energy can be extracted using a specially designed pump, which will bring the seawater up to the pressure required for desalination. That's about 800 pounds per square inch. The pump is designed to operate with small or large waves. This is accomplished using a uniquely designed variable leverage pump, or VLP. Looking at this model of the VLP, we see an actuator float, a reciprocating pump here, and a lever arm, which pushes the pump's piston rod here, all mounted on a floatable sinkable platform consisting of these two cylinders. The lever arm, empowered by the actuator float, moves through an arc of about 160 degrees, 80 degrees in either direction, from top dead center, which is right here. The fulcrums of the lever and pump are offset vertically, and this is what creates the variable leverage feature. This is the fulcrum of the lever arm. This is the fulcrum of the pump. This is the offset between them. The greater this offset, the greater the leverage change for a given arc of motion. The offset of this 1/24 scale model here is 1 inch. The leverage arm is 7 inches, for a minimum leverage of 7:1, which happens when the lever arm is at maximum offset, like this. Here's top dead center here. At top dead center, the force arm has maximum leverage, but only little movement of the piston rod. As it moves away from center in either direction, the leverage is progressively reduced. Thus, small waves are able to power the pump, pumping a small volume of water. Bigger waves will pump more volume as the actuator pushes the force arm farther and farther away from the center. In general, as the actuator float moves, the force arm moves the piston rod of the pump. Thus, the changing leverage regulates the sweep of the force arm and stops the movement when the mechanical advantage is exceeded by the pump resistance. Here are some test videos of the model in a bathtub and also in seashore settings using natural waves. In the bathtub, a paddle is used to create waves which activate the pump. The boat cross-section shaped actuator float seems to deliver the most action, followed by the ball float and lastly by the paddle float, which only works well in breaking waves. The concept of using wave power to desalinate water is not new. In 1978, C.M. Pleece at the University of Delaware described a method for doing it, with a simple float, anchor, and pump called the Delboy system. In the Delboy system, a pump and float are tethered to an anchor on the seafloor. When the float moves up and down with the waves, the pump is actuated. Later in the 1980s, experiments were conducted to prove the concept. Unfortunately, it yielded little fresh water, being limited to the fixed force of the spherical float. In my VLP system, this limitation is overcome because the force is always sufficient to actuate the pump, because the leverage adjusts in accordance with a wave amplitude. The shape of the actuator also reacts powerfully to the slope of the waves. Other features of the VLP system include a floatable, sinkable platform. When in operation, this rests on the seafloor while the actuator floats on the surface. When compressed air is blown in, water is ejected and the platform floats to the surface. This feature makes it simple to move the VLP to other locations. The VLP will also be fitted with bladder accumulators to regulate the pressure within the system. There will also be pressure release valves in case of overpressure. It makes sense also to locate the RO filter ashore where it can be serviced. Thank you for watching this video. It is my aim to develop an inexpensive method to purify seawater for human and agricultural uses. I plan to build a small working model of the apparatus that will use a small hand-operated desalinator powered by the VLP. If you want to help in developing this vital technology, please donate to this fundraiser or to Venmo at Joe-Tate-18. Thank you once again for your interest in this technology that might help fight climate change.